Swayam Prabha. Digital India. Educated India.
So, as you understood, one of the big issues of working with multiphase flows is the fact that we have multiscale physics. So, we have, let's say, and what I'm going to describe here is the work that I have done during, let's say, is not historically. It's a kind of my career plotted in this kind of axis about the scales. Okay? So, I worked on nanoprinting. So what is happening when the droplet of nanodroplets are impacting a surface? I work with nucleation models. This is my work now, my main research field at the moment, because I started with droplets and so on, and then of course I recognize, okay, I need boiling. I need to understand something more about what is happening at the nanoscale. Otherwise, I work with microfluidics a lot. Now I'm working, yes, I show to you the fact that we are working with alginate droplets inside the system. Of course, I work with pool and flow boiling. Drop physics, this was my PhD thesis. My PhD thesis was about droplet impact. I work about icing phenomena, for example, to avoid icing on the airplane wings using hydrophobic, super hydrophobic surfaces. I'm working about heat pipes, and here we are at the millimeter scale. And before, microfluidics between micrometers and millimeter, depends on the system. But I work also about building physics a little bit, because there was a course in my faculty about building physics, and who is doing this course? Who is doing this course? Marengo, are you doing it? I don't know anything about buildings. Okay, you can do it. You must do it. Okay. I'll do it. And then this is my master degree thesis. It's a very big multiphase flow called universe. In fact, my master degree thesis was about the large-scale structure of the universe, where the particles were the galaxies. So, in fact, this was my first multiphase flow in my career, in my scientific career. In fact, I am a cosmologist. So initially I'm a cosmologist, then I changed, but okay. So in fact, my career, sometimes I'm asked to deliver, let's say, a plenary lecture on my career and so on, and I start in this way, to describe all what I've done during the years, and that I'm covering really all the scales. This is really amusing. But what is happening when we are going to do simulations? We need to think not only about length scales, but also about time scales, first of all. Okay, so when we are dealing with molecular dynamics, we are speaking about from Armstrong to nanometers. With the molecular dynamics, we can go up to 100 nanometers, maybe. Then it's becoming quite challenging in terms of computational times. Okay, and we are dealing with picoseconds. Then we have coarse-grain MD. So we are trying to put together a group of molecules, let's say, and then in this case we can go a little bit higher, let's say maybe 200, 300 nanometers, something like that, maximum. And we are speaking about nanoseconds. Then we have the kinetic modeling, again the same scale, but the time is longer. It's about from a little bit lower than microseconds. Then we have the diffuse interface, stochastic hydrodynamics. We are going from nanometers. My simulation has 2 nanometers, 3 nanometers as a limit, right? Up to, I was very optimistic here, let's say 1 micron. Yes, stretching the system and waiting a lot of time. Then you may do it. And the time scale is about nanoseconds. Then we have the phase field. The stochastic fluid mechanics is something inside the big realm of the phase field. The phase field is nothing else than solving Navier-Stokes equation when we are considering an interface that is diffused. So we have a length, a finite dimension of the interface. In this case, with phase field, with different degrees of accuracy, we can go from nanometers to millimeters, so it's quite promising. And then we have the VOF, level set method, or the hybrid methods that are going from micrometer to millimeter. Just now with the PhD students, we are trying to understand which is the lower limit of VOF. So if you're doing VOF, and instead of a nice droplet of 10 microns, of 100 microns, or 1 millimeter, we are going to 0.1 microns. What is happening? Is able OpenFOAM with VOF to solve this kind of problem? Which is the factors that we need to include? For example, we saw that the problem of the density is quite important. So, for example, if you are going below 1 micron and you are still using VOF with the incompressible code, you may have big problems. Okay? So this will be a next paper that I'm going to write with my colleagues. Then we have lattice Boltzmann with a very versatile way to solve many problems with a different scales. The main problem, there are problems with lattice Boltzmann related, for example, that is not reproducing the sound velocity. This is, someone said that it was solved, but I'm not sure because I didn't find the paper where this problem was solved, honestly. So I need to check. And there are problems with the interfaces, let's say, the inaccuracy for some phenomena and so on. But it's, of course, very interesting. I'm not a specialist in lattice Boltzmann. I don't know anything. Okay, so I don't want to enter because I never touch it. I know that because I'm receiving papers and so on as an editor, but it's not really what I'm. And then there is a big, point is about the Lagrangian Eulerian or Eulerian simulations that are going even to meter even more. Okay, so very big simulations. For example, even for atmospheric conditions, so we are speaking about kilometers, not only meters. So in fact, so what we have, there are, let's say, different scales. One is the electronic scale, even quantum mechanics. Then we have the atomistic scale level to describe the phenomena, statistical mechanics. Then we have the mesoscale level, and then finally the continuum level. In this here in this Gian course, we are going to speak only about continuum level. So I'm not going to speak about mesoscale, and I'm not going to speak about statistical physics and the other things. So the phenomena inside the multiphase flows, as we understood after 4 days, are very, very complex, are really very complex. It's one of the most challenging phenomena that you may describe using CFD. So we can distinguish at least two big kinds. So inside there is the word, but we can say on one side there is a global Eulerian multifluid approach, can be Eulerian Lagrangian, but it can be a way to treat multiphase flows. And so the continua, so gas and liquid, gas and particle, are interpenetrating, so they are flowing there inside. And of course, what is important, so we are not tracking in this case, we are not tracking the form of the interface, for example, the bubble and so on. For us are particles, okay? We are going to see the equations later on. But what is important in this case then, if we have two components flowing, is the interaction between the two components. So what is very important are the closure equations to describe the coupling between one phase with the other. So then it's becoming very tricky, the closure submodels, to know the closure submodels. And then there is another way, that is a so-called direct numerical simulation, where we are really looking at the evolution of the interfaces. We are writing the equation in a way that is possible to track what is happening in time and space at these interfaces. The Eulerian can integrate the Lagrangian aspect, so this means that the particles are going to be simulated as a trajectory inside the continuous phase. For example, when we have dispersed phase. About the Eulerian methods, we have advantages. We have a smaller number of computational cells. We have higher computational time steps. So it's easier. And of course, this is very good when we have big scales. So large scales, industrial problems, so on. These advantages, of course, is a little bit difficult to write the interaction exchange terms. You will see from the equations. It's not easy. Sometimes it's very difficult to include all the physics inside. Okay. The second point is that you need to use maybe empirical correlations. And for example, for the interfacial forces, and usually we are dealing with average flow parameters, and this is becoming quite tricky when we have turbulent flows. For example, when you have let's say boiling flows, let's say, of course, we are not looking at the bubble nucleation. We are not going to have a bubble rising because we are not tracking this. So for us, it's something like producing the dispersed flow, bubbles, and tracking the bubbles inside the flow, like an interpenetrating continua, but we are not dealing with what is really happening in this way. It's possible to have a good approximation, but we rely on the closure semi-empirical or even empirical equations. For example, for the H. So we are not we are coming back to the convection coefficient. So we don't know what is happening exactly, but so we are treating the boiling when we are giving a given H. So we are giving a given value for the transfer coefficient, which consider everything inside. But of course, then we need to rely on the empirical correlation for the H in the boiling conditions. The direct numerical simulations are really able to predict what is happening at the interface. We can include a lot of physical mechanisms. Heat transfer, mass transfer, Soré, Dufour, Magnus effect. So we can really put a lot. Safman, everything can be included, okay? Which is not bad, of course. So we don't need, in principle, to have, let's say, submodels. However, in most of the direct numerical simulation, at a given point, for multiphase flows, we need to have tuning parameters. For example, for the boiling, we come back to boiling, and you are doing boiling with the VOF. The only things that we can do, we can say something about the surface is that, we have a surface, but we are not able to solve the roughness of the surface. The roughness of the surface is a scale that is maybe beyond what we have. No? So then what we can do is to patch initial vapor seeds on the surface. And from the initial vapor seeds, we have the boiling. But we cannot have a simulation that is saying, how many bubbles we have on the surface and so on. Then when we have the bubble seeds, then we can have the growth of the bubbles, and then we can have the simulation. But again, we need to rely on the fact that we don't know what is happening before. This was one of the major reasons why I started to study statistical physics and doing the mesoscale simulations. One big disadvantage is the huge computational power that you need to have, okay? Especially if you want to resolve the problem in a very accurate way. One of the issues that I see as an editor of journals is that many times there are, let's say, they are coming to me, let's say, papers with simulation, for example, of boiling with, let's say, 50 or 100 micron mesh cells, the size of the mesh. It doesn't work. Yeah, but the mesh, I did the mesh, for example, the sensitivity analysis, and they didn't change. Yes, it didn't change because you are still very far. So this is the point. So, so you need really to, for example, for a very accurate simulation of the bubble rise in a kind of condition, you need to go up to 2 micron of the cell size to understand what is happening. For example, look at you, this cavitation is like that, 2 microns. So this means that really, if you want to simulate something big, big means millimeters, big millimeters, and not more than that, it's becoming quite challenging. And then, of course, because of the very small cell size, we have also very small time scales. It's not unusual that we are going time steps of nanoseconds. It's not unusual, even less. So This means that we can work on that. We are not including the mesoscale effect, and we can use it when we have a small domain. Few droplets, few bubbles, microchannels, then it's possible. If you go up, no, then it's not working anymore. It depends. We have also meshless methods. For example, the SPH, the smoothed particle hydrodynamics, which in fact is a mesh-free Lagrangian method, which is interesting because it can include a lot of physics inside them. So it's quite powerful. And there are, let's say, problems, for example, related to the surface tension. But for example, if you have problems like, you know, the breaking of the dam, the classical problem that you have water, a wave, a big wave. This is not too bad. It's also a possibility to work with SPH. I'm not going to say something about that. What is in the last few years, the SPH became very interesting because of the GPUs. Because the ways to treat the equation in SPH can be really interesting for the use of the GPU. The CPU can accelerate the simulations, and this is so interesting. It's becoming now interesting. Before it was okay, interesting, but until a given point, the surface tension is not there. Other phenomena are not included. Now it's becoming more interesting because, of course, with the GPU, it's not too bad. Especially if we have many different components. So we have particles of liquid, solid particles, particle related to the gas, particle related to another liquid, for example. Then it's becoming interesting. And now with the GPU, it's becoming even more interesting. Again, as I said, there is a problem with the surface tension. There is a colleague of mine that is working on that. Well, we have errors, we have spurious currents, so the interface are not well described and so on. But someone is working. I think one of the strongest group is in Munich, in Germany. They're working on that, and they are doing something also with surface tension now. Gas-solid flows. So, as I said, there is an Eulerian approach. So both phases are considered, let's say, flow, in a flow with the Eulerian treatment, and then we have Eulerian Lagrangian approach. The Eulerian is, let's say, somehow easy in the sense that we have the equation for the water, for the liquid, for the gas, and we have an equation treating the solid particles as a flow, as a continuum flow, okay? Which is possible when we have, for example, a lot of particles. For example, as you saw in the image before, we are going to have a lot of small nanoparticles inside the mixture, for example. And then we are stirring, and we would like to understand what is happening. Of course, the two things are going to, let's say, we can separate them, and then we can calculate what is happening. Of course, here what is important is the link between one phase and the other. And then we have Eulerian Lagrangian approach, and here we have at least 4 different kind of solutions. One is the discrete phase model, DPM. Okay, discrete phase model is tracking, let's say, the particles. The particle-particle interaction are ignored, but the interaction between the continuum phase and the particles is there. Okay, then we may have a better, let's say, discrete phase model where we have also the particle-particle interaction inside, so we have the collisions of particles, and we can consider hard spheres or, for example, soft spheres. Okay, so we can have different cases. So we can put elastic and unelastic collisions in the simulation. We have the so-called discrete element method, DEM, with a soft sphere in this case. So it's interesting because we can, in this case it's interesting because, for example, we may have heat generation due to the collision. Okay, so we have a soft sphere, so we can calculate the formation somehow. So in this case we can calculate how much is the heat due to the interaction, which is not possible with other methods. And then we have, let's say, the multiphase particle in cells, MPPAC, where, let's say, we are going to have a very good, we are considering in a very accurate way also the viscous interaction. So all these methods are differentiated by how they treat the particle-particle interactions. So let's start with the Eulerian approach. As I said, the Eulerian approach, the fluid and particles both are considered continuous phases. Here we are using the concept that we had when I spoke about the multiphase flows, number one. So we are speaking about volume fractions, okay? So the volume fraction, to track the values of the volume fraction is really the key point. So we know how much is the volume fraction of particles inside the total volume, I say, and these values are changing in time and space during the simulation, okay? Of course, the sum of the volume fraction must be 1. We have already seen that. And we need to write the conservation equation. For example, these are for the Euler to fluid model. We have the conservation equation, and you can see they are completely separated, as I said. You can recognize what we have demonstrated. We had demonstrated when I did lesson 2.1 about this, the modeling of the Navier-Stokes equations, the conservation methods. And we can write this term here. This is the mass conservation, and this is the momentum conservation. Momentum conservation is quite classical. However, classical until a given point, because, for example, we have this beta US minus UG. So this is becoming not completely separated. So because we don't have the pedix G all over, but there is a first connection between particles and the liquid or the gas, okay? The same here. So the two equations apparently are, let's say, the classical Navier-Stokes equation, but we have now here another term that is already a first link between the two phases. So one of the points is that tau G and tau S, in fact, let's say, can be written again in this way. And the problem is that, and this is beta, sorry, is the closure equation for the beta. The closure, when we are speaking about closure equation, means that which is the link between the solid particles and the fluid, the continuum phase, and can be written in this way. And in fact, it's linked to the drag coefficient of the solid, the particles that are going to be dragged away, or let's say dragged with the flow, okay? And this is the terms for the that we have for the gas and for the solid, and we can admit the fact that we may have, as you can recognize, even a compressible situation. And this is interesting. Look, the compressible term is in the solid. This is interesting to point out, because imagine to have a fluidized bed with a lot of solid particles, and we are considering the solid as a fluid. Okay? Well, it's really possible that the density is changing. So we have agglomeration. And so this means agglomeration for the solid means a change in the density. So in fact, it seems strange to say, but the fluid, gas, and liquid is incompressible. Maybe incompressible. The solid is compressible, which is a little bit weird. What? The solid? No, the solid the fluid is incompressible. No problem. We can deal with this. The solid is compressible because we have agglomeration. We have the fact that the particles can stick together. So in a volume, you have more particles. So in fact, you are changing the density. And then we have the energy conservation equation, and this is also this is for the solid part, and so we can have something similar also for the other one. Another point that we need to simulate is which is the pressure of the particles. We said that is a flow, no? So imagine to have all these solid particles. And so is if continuous, then there is a pressure associated to the continuous, no? Like the fluid, like water, liquid water or gas. So we can write the pressure in different ways, but this is a possible way. It's linked to the temperature, for example. So we can construct an equation that is saying how much is the pressure of the solid linked to the temperature of the system. We can even write the viscosity of the solid. This is one way, because here we are entering in the research domain. So we can have different kind of equations in order to describe what is happening for the different particles. For example, if the particles are solid spheres, it's something. Someone is adding now, oh, but it's not our polymeric, ellipsoidal particle. Then you need to change a little bit. So we are entering in research. So there are really very sophisticated models for the different cases. And even which is the conductivity, the thermal conductivity of the solid flow. So you need to write expressions, and this is again only an example. I took an example from a paper, how to write pressure, viscosity, and thermal conductivity of the particles. Then we have the Lagrangian approach. We have a lot of commercially available codes and so on in ANSYS, OpenFOAM, and so on. What is important here that we are going to have a continuum flows plus the disparate flow that we are tracking using the Newton laws of mechanics. So we are going to have equations that are, let's say, linking the m of the particle, acceleration of the particle, the square, the x, the t square, equal to the amount of forces acting on the particles. And so in this case, we are going to have the particles going around, and the trajectory of the particles are inside the simulations. What is interesting is that when we have this kind of solutions, it's not too bad if we have also not only a sphere, because the other one is relying on the fact that we need to write the right equation for the thermal conductivity, viscosity, pressure, which is a mess. Here we have a particle that is going around. It's not too bad, for example, even if there is a different form, this is okay. It's not a problem at all in this sense. We can even have angular momentum of the particles. We can include, because it's a question of balance of forces. So we can have also the conservation of the angular momentum of the particles. So we can have cylinder. We can have particles as cylinder that are rotating in the space. It's possible. And for example, for a spray, we can use this one. Because for the spray, we can use this kind of simulation. So the spray is producing a disparate phase. A lot of drops are going away. One of the problems, of course, is you can already imagine that Eulerian Lagrangian simulation can be really overwhelming if we have a lot of particles. Because we are following each of the particles, so it's becoming really crazy. So what is happening? We can have a coarse-grained Eulerian Lagrangian simulation. What does it mean? Instead of following each particle, which can be overwhelming, okay, we are building up parcels. Parcels are a group of particles together, okay? So, for example, in the case of a spray, we can put together the particles with a given dimension. Because the spray is producing a distribution of droplets, we can say, okay, we can try to have all together and in small packets, and see what's happening. So this is interesting because in this case, even if we have really a lot of particles, we can have, let's say, we can follow not the particles but the parcels. Someone is calling also digital particles because they are digital. They are not. It's a set of particles. The parcels are working in the way that the digital particle is going to have the given temperature, the given properties. one parcel, one property. So we are collecting 1 million particles with the same property that are useful for our simulation. And we can, in this case, have a very interesting simulations and so on, okay? And let's say one of the problems, of course, if there is the collision models, for example, in this case, parcel, the same for the sprays. The parcel of droplets are going with another parcel of droplets is coming, and we have another new parcel, or maybe two parcels, but with different properties because of a coalitions of droplets, or maybe breakup of the droplets. So the parcel itself can change due to the collisions, okay? And this is, of course, a problem because, again, we need closure models to understand how to deal with the variation of the properties inside the parcels. How is possible to write the equations? Well, again, is too long here, but we are writing, let's say, the classical equation where we have the position of the particle that is linked to the velocity of the other fluid and the forces that are acting on the particle. I'm not entering. There is a lot of literature, let's say, at the end. Then gas-liquid flow. The gas-liquid flow is very complex because we have the surface tension. Every time that we have a liquid, we may have the problem of the surface tension. We may have, in the sense that, of course, if we have a pipe and you have full of oil and the oil is flowing, there is no problem with the surface tension, of course, okay? When we have a flat surface, it's not a problem with the surface tension, okay? However, every time that we have the presence of something else, gas, we have a free interface somewhere, can be a bubble, can be wavy, film and so on, so the surface tension is playing a role, and we need to consider it. We cannot more say, okay, we can neglect, okay? Also for the gas-liquid flow, we may have Euler and Euler-Lagrangian simulations. Again, the point is, as I said before, is that we need to have the right closure models. Another point is that solving this, let's say, the problem of gas-liquid flows is quite complex because there are really a lot of possible scales. In small dimension, we can go for the direct numerical simulation. In big dimension, for example, heat exchangers, we need to rely on Euler and Lagrangian. So otherwise, it's too big. But for example, in microchannels, the phases are very well separated, so we can work on that and we can do the simulations. So at the end, the picture that I like this paper from Martin Werner. We have the Lagrangian type and we have the Eulerian type. And what is important in this case is to understand how to deal with the interface. Interface is the devil. So it's the way that we are dealing with the interface is becoming, of course, the key point. Okay? So there are different ways. First of all, we have, let's say, two big distinctions. One is about the zero interface thickness, so the interface has no thickness. Okay? It's really like a mathematical interface. Okay? And the other one is when we are accepting the fact that we have a finite dimension of the interface. For example, in phase field. Okay? Or there are, let's say, different form of the VOF, for example, can be with, let's say, if you are allowing in VOF to have a given interface thickness, we can play with this, especially, for example, if we have VOF simulation very close to the critical point, this can be a problem, or we are dealing with VOF with compressible codes. So then, in this case, we need to understand how thick is the interface. Otherwise, with zero interface thickness, we have different way to explore the simulations. And this is the moving mesh. So we are moving the mesh with the interface. We have the front tracking, level set methods, and the VOF where we have a very sharp interface. Of course, all this situation may have problems with the, for example, with the VOF. If we are doing a very sharp interface, we may run in the problem that we are losing mass. It's a very classical problem in VOF. Okay, so we need to tune the things, and we need to have the right value of the right shape of the interface in order to avoid problems like that. Nowadays, we are really able to have a very good VOF, for example, also level set. Now, I don't have time to explore all the different ways. This was a very old way that was used, let's say, years ago, Marken and cells, which was a way where we are going to have, we mark at the beginning points on the interface, we have the droplet. We mark, and we are following where it's going, we are going these points. So this is the reason why it's called Marken and cells. So we are writing equations where, let's say, we are a kind of transport. It's something like solid. Imagine to have solid particles on a droplet in some points, regular points. And we are following the solid particles. Solid is not solid, it's a mathematical point, but we are following them. And so the bubble, or let's say the droplets, is changing the form because we have, let's say, the relationship related to the trajectory of these particles. Then we have all the methods linked to the front tracking. Let me see, because the front tracking methods, like we have the Lagrangian frame. So in fact, this is done using a mesh that is changing the form. So it's the mesh that is following the interface. So in the other cases, the mesh is fixed, or we can have mesh refinement. So I mean, we can have all these kind of techniques, but there are numerical techniques in order to improve the accuracy close to the interface. No? In this case, the mesh that is moving. So the concept is a little bit different. It's very accurate in terms of surface tension. For example, if you want to understand something about the variation of the form of the droplet when we are putting a sessile drop and so on for the different contact angles, well, there is a code called surfer code. The surfer is doing this, so it's only looking at the interface, okay? And there is not so much physics inside, but for example, one of the problems that we have when you're using level set, VOF, this kind of methods is to get the right value of the capillary pressure. It seems stupid because, sigma divided by, 2 sigma divided by R, 2 sigma divided by R, no? I'm always in mind sometimes sigma divided by 2R. I don't know, sometimes I need always to think 2 sigma multiplied by 1 over R, 2 sigma divided by R. Yes. So we know the capillary pressure, right? Well, if you're using VOF and level set, you are close, but not exactly. With these methods, you are exactly there. Then we have arbitrary Lagrangian or Eulerian. Don't have time for that. And then we have volume of fluid. We are going to see in the second part volume of fluid a lot. It's kind of my specialty. So this is the reason why I put a little bit more. I have also videos on that, so it's interesting. The VOF. These are simulations with the VOF. I think that everybody saw that. At the moment, I believe the VOF is the most popular interface capturing approach. Okay, level set is pretty much used also. Okay, they are somehow similar, let's say. Okay, but of course different techniques, but similar. We are going to speak about that later. This is the level set. So in the big difference is really the form of the equation, how we track the interface. In the case of the volume of fluid, you are going to see the equation. We have a color function that is saying is a volume fraction, and we are having an equation for the volume fraction. In the case of the level set, it's not really a volume fraction, but is a kind of distant position. So we are going to have a change from a phase to another. So we have a given form of the density, for example. Imagine to have the density, and we are going to check where the steepest gradient of the density is. So we are going to have where we have in this distance function the points in the domain where the distance function is equal to 0, means that we are in the position of the interface. And we can say this is the position of the interface. And these are, again, animation of the level set. And let's say, also this method is quite used and so on. This is on the right. We have even film boiling phenomena, for example, because in both methods, of course, we can include the energy equation, so we can consider, let's say, heat transfer and so on, boiling. We can even combine. The VOF is mass conservative when we are allowing to have, let's say, a value for the alpha that is free. But then we will, if we like to define the interface, in the way that we are defining the interface, we are changing the mass. Okay? So inherently, the VOF is mass conservative, and the interface is diffusive. However, in practice, since we would like to see a nice interface, we are using methods to reconstruct the interface in VOF, and then we are losing mass. In the LS is inherently, so originally, is not mass conservative, but it's very good for tracking the interface, so a very sharp interface. Because the interface in level set is a mathematical point, is when the distance function is equal to 0. So this means that we have a nice interface. Okay, but we are losing mass. So both systems at the end, we are going in different direction, but they have a problem with the mass a little bit. Okay, so if you are putting together, we may have nice simulations. And for example, this is a simulation of the splash. Yeah, okay. This is coming. And the simulation is not bad. Well, this is for the milk with different parameters and so on. And honestly, this is a very good simulation because it's possible to see even the perturbation on the lamella. So not bad. There are different cases, different velocities. We have the breakup and so on. What is important to say with these methods is that, for example, when you have one droplet and that is colliding against another droplet, we have drop collision. Okay, sometimes we have the bouncing of the two droplets. So the two droplets are arriving, but they are not going to coalesce. Okay, so this is the bouncing of the droplets. Where with the VOF level set is quite difficult. Why? Because what is that? Ah, yes, it's still the video is going. You are distracted by the video. Because I was looking, nobody was looking at me. What's happening? So, what I want to say? Go? Ah, yeah. Pay attention that one of the problems is the numerical coalescence or numerical breakup. So, if you have, for example, in the splash, if the lamella in the crown is going to be very, very, very thin, you are going to have a breakup that is not the real breakup. In the reality, it's not happening. But it's happening because we are going to have the liquid film that is below a given thickness. For example, 2 mesh size, 2 cells. And then, of course, we have a breakup, but it's not real. It's numerical. So this means that we did something wrong with the dimension of the cells. Okay? Same thing, even trickier, is when we have a droplet impact with rebound. Because when the droplets are arriving together, Of course, there is one point where we have the liquid from one side and the other. And so then we have the correlations for the numerical work. But in fact, it's not, because we have the presence of the air inside between the two droplets that is going to, let's say, to avoid the coalitions of the droplets. And so the droplets are colliding and they're going away. It's possible to see it. And this is difficult in VOF because you need to have a very, very small scale in order to understand what is happening to the gas air. And the phenomenon is with a gas that is compressible. So the only way to simulate correctly this phenomenon is that, which is very simple, droplet-droplet impact. I mean, it seems simple. In fact, it's not simple. It's really to have a simulation with compressible gas and very, very thin mesh, because we need to understand what is happening between the two liquid interfaces. Lattice-Boltzmann is I know that it's a powerful numerical tool. In my life, I never did this, so I'm not an expert, and I don't want to pretend to be an expert, really. I don't know. I know that many people is using it, and I think that it's working, because as an editor, I saw papers coming, and I saw the results, and the results are quite good. But I'm not an expert, so sorry for that. Phase field method, yes, they are based on the fact that we have the conservation equation where we are allowing to study also the interface. Okay, and this is very interesting. Is a novel approach in the sense that Canhillier is quite well known, the Canhillier equation, but more and more is used also for, let's say, for simulation of droplets and so on, when we have, let's say, the situation where the interface may have a dimension, okay? For example, close to the critical points and so on. So can be quite interesting. Let's write, for example, for the VOF equation, let's write the governing equation. So we are considering the fluid incompressible, okay? Divergence of U is equal to 0. Done. Navier-Stokes equation, we can write down the Navier-Stokes equation, and then we have so with the different forces and so on, and then we have the volume fraction. This is the main point. So we have the volume fraction transport equation. So see that here, the mass continuity is expressed by the divergence of U equals 0. So this is becoming now the transport of the two components. This is becoming now the transport of the two components. So using the volume fraction, using alpha is the color, sometimes we call color function, but in fact is a volume fraction. Okay. And then what is important using for this in this model is that because we have the volume fraction, all the properties can be averaged linearly with alpha. So, for example, the viscosity of the bulk can be a linear function. So, with this kind of rule, it's called a leverage rule. It's called leverage. Let's call it this rule in English. Leverage, I think. I don't know. Okay, it was a way. Okay, but you know, for example, also for the enthalpy in two-phase flows and the enthalpy, entropy, and so on. There was a way. Forgot. Well, if you notice this, we have a difference between what I said the first hour. Because in the first hour, I put the surface tension as a boundary condition. And they said, it's not important what is happening in the momentum equation, what is important, the boundaries. Now, I'm trying to do this kind of work. I'm trying to put the surface force inside the Navier-Stokes. So there will be a boundary condition, of course. But I put the force inside. So the force, the surface tension is a force acting in the momentum equation. Which is, in fact, we know the force, because we know let's say that is 2 sigma divided by r is the pressure. If you multiply by an area, we are going to have a force. Okay? But it's tricky, because this force is only at the interface. We need to put in a way that the force in this Navier-Stokes equation is switched on only where we need. There are few cells in the domain. you can understand already where is the change. What we can look at the gradient of. No, the surface tension is a parameter. No, but in this equation, if we would like to switch on this term, the gradient of alpha. The gradient of alpha. The volume fraction is alpha. So the gradient of alpha is going to decide where we can switch on and off this term. So in fact, what we can write is that we can write in this way. So we can write that the force is a surface tension multiplied by K, the curvature, multiplied by the gradient alpha. This is the way to say all over the bulk is 0. Only we have a gradient, we are going to have surface tension. Not only it's possible to write the curvature in the way that is expressed by the divergence of the gradient of alpha, which is interesting, because together we have already the curvature. And the point is that at the end what we are landing to have is that we are going to have a lot of 0, where is one, for example, component, for example, gas, and where we have 1 is the pure liquid. We have only liquid. In between there is a value, okay? This value means that it's not that because we have, pay attention, it's not that because in these points we have liquid and gas. It's not the quality, it's not the vapor quality. Forget. It's only that numerically we know that inside these yellow cells we have the interface, because there is the variation of alpha, of the volume fraction. Nothing to do with the vapor quality. So we know that something there is happening. We can live with this. We can say, oh, okay, it's fine. We can have these points with the given value of the volume fraction. It's not a problem. However, sometimes we would like to have a reconstruction. Here is very clear. We may have something like that. But again, can be something like that, can be something like this one. So we don't know exactly, because it depends on the value of the alpha that we have inside. For example, here can be 0.1, 0.9, 0.7. So 0.1, 0.9 means that, oh my God, so there is a big difference inside these cells. 0.1. So we need to reconstruct the form following the values of alpha. This method is quite important. It's very important. For example, in order to avoid so-called spurious currents, so there are, let's say, velocities that are, let's say, generated by the fact is an artificial velocity generated at the interface by the effect of this kind of assumption. In an open form, for example, we have different ways to solve the VOF with an interform or with an interface sharpening. So I think that are, let's say, possible ways. And in level set, if you see the equation is similar, okay? So we have a level set function. And why the level set is inherently very, very good in terms of interfaces, on sharp interfaces, because before I said, VOF is very good in mass conservation, but a little bit worse in terms of surface reconstruction, let's say. But because the interface is diffuse, but we can reconstruct, so we are coming back to the mass problem. Okay. Here, why? And you can see that because here we have directly this equation. See? So the surface tension force is really written in an explicit way. So in this sense, inherently, level set is better for the interface and worse for the mass diffusion. At the end, they are very similar, because also with the VOF, after reconstruction is going to be somehow worse. So then when we have the classical mass diffusion. And so we can write the different forms of the interface curvature and so on. Again, I don't have time to enter in the details here. I left these slides for you. And so